Today we will talk about an interesting problem. This is a maximum flow problem using Fulkerson algorithm. My name is Abdullah Rafi. I'm a student of Noakhali Science and Technology University. So first of all, what is maximum flow problem? This is a problem for finding the maximum flow between any two vertices of a directed graph. The efficient way to find the maximum flow of a graph or network is Fulkerson algorithm. It is also known as Fulkerson method. Fulkerson algorithm is a greedy method and it is published by L.R. Ford and D.R. Fulkerson in 1956. First, you need to know some terms to understand the problem briefly. First, we have to understand what is source. In a directed graph, a vertex that has all outward edges and no inward edges is called a source. Here in this graph, we can say this graph as G. The graph is G, and for this vertex, there is two outward edge, but there is no inward edge, so it is called source. And what is sink? A vertex that has all inward edge and no outward edge is called sink. Here in this graph, T is sink. And what is capacity? Capacity is simply the weight of between two vertex. And we can let S is one vertex and P is one vertex. So the weight between this, there is a H, and the weight of the H is 5. So this is the capacity. And we have to understand what is bottleneck capacity. A bottleneck capacity is a minimum weight of a graph. Let us assume there is a path from source to sink. The path we can consider as S to A and A to T. So for this path, this is the path. The minimum weight is 7. So this is the bottleneck capacity. An augmented path, if there exists a path from source to sink, the path is called augmented path. And residual capacity. The residual capacity is the original capacity minus current flow. If let us consider for this B to T, the original capacity is 9. Here the original capacity is 9, and let us assume that flow is 4. Then the residual capacity will be 9 minus 4 is equals to 5. This is the residual capacity. So what is the algorithm to solve this problem? Initially, we mark all the edges, the flow of all edges as 0, and while there exists an augmenting path, the minimum flow or bottleneck capacity will be added to the maximum flow, and we will return it. We will terminate this work until there is no augmented path available. This is the algorithm. So for better understanding, we will see an example. This is our graph. Here S is our source and T is our sink, and we have to understand what is the maximum flow of the graph. So how can we solve this problem? First, we have to find the paths, the available paths of this graph. So first of all, let us choose a path. The path is from S to V1, V1 to V3, and V3 to V2, and V2 to V4, and V4 to T. That is our sink. So the minimum flow of this graph of this path, or bottleneck capacity is this is 16, this is 12, this is 9, this is 14, and this is 4. So the bottleneck capacity will be 4. So and the flow will be 4. Flow for this augmented path will be 4. So 4 will be written left side of the original capacity. This is the original capacity. So with the maximum flow, the flow will be added. The maximum flow, initially the flow was 0. The flow was 0. The flow was 0, and 4 will be added to this maximum capacity, and then the graph will be updated, and for this the residual capacity will be 12. It will be 8, because 12 minus 4 is equals to 8. 9 minus 4 is equal to 5. This will be 10, and this will be 0. 4 minus 4 is equals to 0. In the second step, step B, we will find a path from source to V1, V1 to V2, V2 to V4, V4 to V3, and V3 to T. So for this augmented path, we have to first determine what is the bottleneck capacity. Now we have to understand that there is also a in this step A, there will be this path. This H becomes 0, so we can backward edge. We can draw a backward edge for this, and the weight of this graph will be 4. Backward edge will be 4, because it became 0, so the backward edge will be 4. So we can draw a backward path from T to V4, V4 to V2, and V2 to V3, and V3 to V1, V1 to source. We can draw another backward augmented path. So for the backward augmented path, the value of the path will be 4, and our minimum path capacity will be, this is the for the path, this is the minimum capacity, so it will be added. So the value will be our residual capacity, our bottleneck capacity will be 11. And for the path, for every edge of the path, the value will be added. 4 will be added. So 12 plus 4 is equals to 16. Here is 16, and here is 8. That was 8, and 8 plus 4 is equals to 12. 12 will be updated. And for this 10 plus for this it was 10, and 10 will be 10 plus 4. This will be 14. This will be 14, and we will write flow on the right side. So this is our flow. 11 is our flow. 11 is our flow. Here 11 is our flow, and the capacity is in the right side, the flow is in the left side. So the bottleneck the residual capacity will be will be updated. 16 minus 11 will be 5, so this will be 5, this will be 8, and second part is this will be 10 minus 7 is equals to 3. For this 14 minus 11, this will be 3, and it will be 0. 20 minus 7, it will be 13. So in the next step, you can see the values are updated. 5, this is 3, this is 11, and this is 7, and this is 13. So values are updated, and in this manner the process will be proceeded, and in the last step we will find the maximum flow, that is 23 for this original graph. And in this section we can see that there is no augmented path available. The application of this problem we can see in fluid in pipes problem, current in an electrical circuit, traffic on roads, data flow in a computer network, money flow in an economy, and etc. Thank you for